74 million. That is how many individual radio signals a team of scientists picked up while pointing their instruments at an object racing through our solar system from another star system entirely. A number large enough that reading them all out loud, 1 per second without stopping, would take more than 2 years. 74 million separate blips in the data, any single one of which could have been the first confirmed evidence of intelligent life beyond Earth. By the time the team finished narrowing that number down, filtering out noise, interference, and anything that could be explained by ordinary human technology, they were left with exactly 0. But the story of how they got from 74 million down to 0 is far more interesting than the final number itself, and it tells us something important about how prepared humanity actually is the next time something like this shows up. This is the story of what happened when the SETI Institute turned its most sensitive radio telescope toward 3I/Atlas, the third confirmed interstellar object ever detected passing through our solar system. And by the end of this video, you will understand exactly how scientists searched 74 million signals in a matter of hours, what those 11 strange signals were that almost made it through, and why the researchers involved are calling this a success story, even though they found nothing at all. Let's set the scene, because timing matters enormously here. 3I/Atlas was discovered on July 1st, 2025, by the Atlas O Sky Survey Telescope in Chile, immediately recognized as only the third interstellar object ever confirmed passing through our solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Within 24 hours of that discovery becoming public, before most of the world had even heard the name 3I/Atlas, a team from the SETI Institute, working alongside the breakthrough. Listen Project had already redirected the Allen Telescope Array, a cluster of radio dishes at the Hat Creek Radio Observatory in Northern California, to start listening. There was no waiting for funding approval, no months of planning. An unusual object was passing through, and one of the only scientific tools capable of detecting a deliberate radio transmission from it needed to be pointed in the right direction while the opportunity still existed. The reasoning behind moving that fast comes from a simple but genuinely serious scientific idea, not science fiction, actual published astrophysics. If any other civilization in our galaxy has ever sent a probe out into interstellar space the way humanity sent the Voyager spacecraft in 1977, a probe designed to drift for millions of years, silently crossing the vast gaps between star systems, that probe would look from a distance exactly like an unremarkable rock or icy fragment drifting between stars. There would be no flashing lights, no obvious markings, nothing to distinguish it from ordinary debris unless someone specifically checked its radio emissions for a signal that nature itself could not produce. With only 2 prior interstellar objects ever recorded in all of human history, and no guarantee a third would ever be found again in any of our lifetimes, researchers involved in technosignature science considered this too rare an opportunity to risk missing, even if the odds of success were assumed to be small from the very beginning. So the team pointed the Allen Telescope Array at 3I/Atlas and began recording across a frequency range of 1 to 9 gigahertz, a band well suited for catching narrowband radio emissions, meaning signals concentrated into an extremely tight sliver of frequency. This detail matters because narrowband signals essentially never occur naturally. Natural astrophysical processes, stars, gas clouds, magnetic fields, tend to produce radio emissions that are messy and spread out across a wide range of frequencies, closer to the roar of static between radio stations than a clean, single tone. A signal squeezed into an unnaturally narrow band is, as far as we currently understand physics, a strong indicator of engineering, of something built on purpose to transmit information efficiently, the radio equivalent of finding one perfectly pure musical note buried inside a wall of noise. If 3I/Atlas were carrying any kind of active transmitter, this is exactly the kind of signal it would produce, and it is exactly the kind of signal the Allen Telescope Array was built to catch. Data collection alone was only half the challenge, because the amount of raw information a modern radio array generates in just a few hours is staggering. To handle it, the team relied on a newly developed search pipeline built specifically for this kind of rapid response campaign. A piece of software designed to process the flood of incoming data fast enough to matter while an object like this was still passing through observable range. Without that kind of purpose-built tooling, a dataset this size could easily have taken researchers months or years to sift through by hand, long after 3I/Atlas had already vanished back into the dark. Over 7.25 hours of observation, using a newly developed data processing pipeline built specifically for this kind of search, the team detected nearly 74 million individual narrowband hits. Sit with that number for a second, because it sounds, on the surface, like an overwhelming flood of potential alien contact. It is not. The vast majority of those 74 million signals were never going to be anything other than ordinary interference, radio noise generated by cell towers, satellites, Wi-Fi routers, airport radar, and the enormous, constant hum of human technology that surrounds every radio telescope on Earth, whether it is pointed at deep space or not. Before we get into exactly how the team managed to sort through 74 million signals in a matter of days rather than years, if the idea of scientists racing against the clock to eavesdrop on an object from another star system is the kind of thing that keeps you watching to the end, go ahead and subscribe now, because the filtering process itself is where this story gets genuinely clever. The first filtering step involved removing what astronomers call radio frequency interference, or RFI, essentially anything that showed the fingerprint of a ground-based, human-made source. Because the Allen telescope array uses multiple dishes working together, the team could compare what different antennas picked up simultaneously, checking whether a signal appeared identically strong across the whole array, the way a nearby cell tower or Wi-Fi router would, or whether it appeared concentrated specifically in the beam pointed at 3i/Atlas and nowhere else. A genuine signal coming from something out in space moving along 3i/Atlas's exact trajectory should behave very differently across the array than a signal originating from a cell tower a few miles away, or a satellite passing overhead on a completely unrelated path. Applying that comparison alone cut the initial 74 million hits down to roughly 2 million, eliminating over 97% of the data in one pass simply by asking whether a signal behaved like it was coming from the sky above 3i/Atlas specifically, or from the ground beneath the telescope itself. 2 million was still far too many signals for any human being to look at one by one, so the team applied a second, more precise filtering tool, a piece of software built specifically to check whether a signal's position and motion in the sky actually matched 3i/Atlas's known trajectory as it moved. A real transmission from the object itself would need to track its exact path across the telescope's field of view over time, drifting at a very specific, predictable rate. Almost nothing does that by coincidence. Running that filter against the 2 million remaining candidates brought the number crashing down again, this time to just 211 signals. From 74 million down to 211 using nothing but mathematics and the physical layout of the telescope array itself, without a single human being manually reviewing a single signal. Only at that point, with the dataset finally small enough to be humanly manageable, did researchers sit down and visually inspect each of those 211 remaining signals directly, studying how each one behaved across time and frequency on a graph, looking for the kind of clean, deliberate drifting line a genuine transmission would leave behind. Of those 211, 11 signals stood out enough to warrant a genuinely closer look, appearing brighter or more distinct within the beam pointed directly at the target than in the surrounding reference beams, exactly the kind of behavior a real, deliberate transmission might produce. For researchers who had spent days processing tens of millions of data points down to almost nothing, these 11 signals were, for a brief window, the closest thing the entire search had produced to a genuine candidate worth taking seriously. None of them held up. When researchers examined the 11 remaining signals more closely, each one revealed a flaw that ruled it out as anything from 3i/Atlas itself. Some turned out to be broader band, modulated signals, meaning they were spread across frequency in a way inconsistent with the tight, narrowband signature the search was specifically designed to detect. Others matched known frequency bands used by human communication systems and satellites, meaning they were almost certainly leaking in from Earth-based or Earth-orbiting technology, despite surviving the earlier filtering steps. Every single one of the 11 was, in the researchers' own words, easily attributable to radio frequency interference. The final tally, after 74 million initial hits, 2 rounds of automated filtering, and 1 round of careful human eyes on the data, was 0 confirmed technosignatures. The team published their full methodology and results in a paper in the Astronomical journal, and one detail buried inside that paper matters just as much as the headline result. A null result, finding nothing, is not the same as learning nothing. Because the search covered a specific range of frequencies with a known level of sensitivity, researchers were able to calculate exactly how powerful a hypothetical transmitter on or near 3i/Atlas would have needed to be for their instruments to miss it. That upper limit came out to somewhere between roughly 10 and 110 watts, depending on the exact frequency involved, an amount of power comparable to a household appliance, something you could plausibly plug into a wall outlet. In other words, this was not a vague, hand-wavy statement that nothing was found. It was a precise, quantifiable boundary, the scientific equivalent of saying, not only did we not hear anyone shouting, but we can prove that if anyone had been shouting louder than a certain volume, from this exact distance, we absolutely would have heard it. If 3i/Atlas was carrying any transmitter stronger than a light bulb, broadcasting anywhere in that frequency range, during those 7 hours, the Allen telescope array would almost certainly have caught it. This kind of quantifiable boundary is exactly what separates modern technosignature science from the science fiction version of the same idea. Researchers in this field are not simply hoping to get lucky. Every search, successful or not, produces a mathematically defensible limit on what could or could not have been present, and those limits accumulate over time, gradually shrinking the range of possibilities across the galaxy where an active, powerful alien transmitter could still be hiding undetected. A single null result on one comet might sound unremarkable on its own. Stacked alongside decades of similar searches pointed at nearby stars, exoplanets, and now interstellar objects passing directly through our own solar system, it becomes part of a much larger, steadily tightening scientific picture. This result did not stand alone either. Earlier in the object's transit through our solar system, a separate search using the Green Bank telescope had already come up empty in a similar way, finding no candidate signals worth pursuing. 2 independently operated radio observatories, using different equipment, different teams, and slightly different methods, arrived at the same conclusion without ever needing to coordinate their answer in advance. Combined with everything else, astronomers had already learned about 3I/Atlas through entirely different instruments, its shrinking size estimates as better telescopes refined the measurement, its slow 16-hour rotation, its outgassing behavior that shifted from carbon dioxide to water as it approached the sun, and the ancient, extraordinarily cold isotopic chemistry locked inside its ice, suggesting a birthplace colder than negative 240 degrees Celsius. Every single line of evidence pointed toward the same consistent answer. This was a comet, an extraordinary one, old beyond easy comprehension and chemically unlike anything in our own solar system, but a comet nonetheless, behaving exactly the way a lump of ancient ice and dust should behave as sunlight slowly heats it from a distance, releasing the same gases, following the same predictable physics that any natural object drifting close enough to a star would follow. One of the researchers involved in this study, Dr. Valeria Garcia Lopez, offered a perspective on the result that reframes the entire search in a way worth sitting with. Rather than treating the absence of a signal as a disappointment, she pointed out that the search itself demonstrated something valuable, that with the technology available right now, today, a real signal, had one existed, would almost certainly have been caught, and that this was precisely why it remained important to keep searching every future object of this kind, even ones nobody expected to be carrying a signal in the first place. The tools worked exactly as intended. The pipeline processed tens of millions of data points in hours rather than months. The filtering correctly separated sky from ground. The 11 false candidates were correctly identified and ruled out through careful review rather than guesswork, each one explained, documented, and closed out with a clear technical reason rather than simply dismissed. Nothing failed here except the presence of an actual alien transmitter, and that was never guaranteed to exist in the first place. In science, a well-designed test that returns a clean, confident no is just as valuable as one that returns a yes, because it tells you exactly where you stand rather than leaving the question open. There is a broader significance to this that goes well beyond 3I/Atlas itself. Before the search, humanity had never actually rehearsed what a rapid response techno-signature search looks like in practice, applied in real time to a genuinely rare, genuinely unpredictable interstellar visitor. Previous searches for artificial signals had mostly been aimed at fixed, predictable targets, nearby stars, and known exoplanets that stay conveniently in the same patch of sky for as long as astronomers care to keep watching. 3I/Atlas was different, a fast-moving temporary guest that would not wait around for a leisurely observation schedule. Now, there's a tested working blueprint for exactly this kind of scenario. The next time an object like this is discovered, and researchers involved in this study are confident there will be a next time, the entire process, from initial detection to redirecting a telescope, to processing tens of millions of raw signals, to filtering down to a final handful worth human inspection, can happen faster and more efficiently because of exactly what was learned here. A negative result on one object still sharpens the tools used to examine the next one, narrowing the margin for error and improving the odds that if a genuine anomaly ever does appear, it will not slip through unnoticed the way it easily could have decades ago. It is also worth remembering just how briefly this opportunity actually existed. 3I/Atlas made its closest approach to Mars in October of 2025, passing within about 19 million miles of the red planet, and its closest approach to Earth came in December of that year, at a distance of roughly 167 million miles, never anywhere close enough to pose any risk, but close enough, briefly, for our best instruments to get a clear look. That window is already closing. The object is outbound now, retreating back into interstellar space along a hyperbolic trajectory that guarantees it will never return, carrying its ancient, ultra-cold chemistry back out into the galaxy it came from. Whatever chance we had to listen for a signal from 3I/Atlas specifically, that chance has already come and gone. So to bring this back to where we started, no, nothing intelligent was found hiding among those 74 million signals. And honestly, given everything else, scientists already knew about this object's age, its chemistry, and its clearly natural cometary behavior. Almost nobody genuinely expected there to be. But the value of this search was never really about the odds of success. It was about proving that when a rare, unrepeatable visitor from beyond our solar system briefly passes close enough to study, humanity now has the tools, the coordination, and the speed to actually check thoroughly, carefully, and within days rather than years, rather than simply assuming and moving on. That, honestly, might be the most quietly reassuring part of this entire story. We did not need to wait for the perfect mission, the perfect budget, or the perfect piece of equipment built specifically for this one object. Existing telescopes, existing software, and a team willing to move within 24 hours of a discovery were enough to search tens of millions of data points and produce a rigorous, defensible, published answer, all without a single new instrument ever having to be built. The next time something crosses into our solar system from somewhere else entirely, whatever it turns out to be, however strange its trajectory or its chemistry, we now know exactly how fast and how thoroughly we are capable of listening before it slips back out of reach for good. There is something worth sitting with in the fact that this entire 74 million signal search, start to finish, took only a matter of hours to collect and days to process on an object that had been discovered barely a day earlier. A generation ago, a search of this scale would have been unthinkable within that kind of time frame. Today, it is simply what happens automatically the moment something unusual is spotted crossing into our neighborhood. A quiet, well-rehearsed reflex built from decades of patient, largely unglamorous work by researchers who spent their careers listening to static in the hope of one day hearing something else. If this kind of deep dive into what real, published research has actually confirmed about the strangest objects passing through our solar system is what you come here for, make sure you like this video and subscribe to the channel, because 3i/Atlas will not be the last interstellar visitor we ever detect. And when the next one arrives, we plan on being here to break down exactly what the data really shows.